Okay, so moving on, our focus now will be to conduct the analysis part of meta-analysis in R. And as you can see here, we have sort of a template that with minimal modification can be applied to pretty much any meta-analysis, given that the data has been coded and put into a table. Okay, so looking at this code here, anything with this pound sign before it is a comment, and that's just to make the code easier to read. And to run any code in R, all you have to do is press Control Enter. So this first line installs the necessary packages, which are basically just bundles of code that allow you to execute different functions that you will need for the meta-analysis. So going over these packages, ggplot2 allows us to plot whatever we get, our results. DevTools is needed to install something from GitHub, which I'll go over later. Pacman is a package manager that lets us load multiple packages at once. So after we install the packages, we must load them into our environment in order for us to actually use the code contained within them. And data.table allows us to make specific data tables that make looking at data much easier. dplyr helps pick apart columns and rows and specific types of data, such as strings. Formatable just makes nicer looking tables that are visually presentable. And the difference between these two is that these are more for visualizing raw data before it's processed, and these are for making it like presentable and nice looking. So let's just press Control Enter and run this. And as you can see here, I already have these loaded in, so I'll get this pop-up here. If you're running this for the first time on your computer, this will likely not show up. So I'll just skip to when everything is done. It might take like 30 seconds or so. Okay, so everything is done, and you can see here that all the packages were successfully unpacked, and they're checked for validity with MD5 sums. All right, so now that those packages are out of the way, if you want to do a multi-level meta-analysis, we are going to install a special package from GitHub called dmetar, and this is why we needed the DevTools package before, because otherwise you wouldn't be able to run this function. And this just downloads it from GitHub. This might take a bit longer, but I'll just skip to when it's finished. All right, it's already finished. I already have it installed, but on your computer it might take a bit longer. Now this library pacman, all it does is it loads the pacman package into our library so that we can use the code contained within. So let's just Control Enter. All right, now we load all of these. So what this does is it makes the code contained within all these packages available for us to use freely. Now what you have to do is within the folder that you should have access to, there's going to be something called codeddata.csv. And you have to just click on that and click import dataset. And it'll come up with a preview where you can see everything and you can change the name. You can really do a lot of cool things with it. But for now, we're just going to click import, and it'll bring us into the it'll bring it into the environment, and it'll also show up here as a sort of a preview. So this environment basically shows all the variables and data sets and intermediate variables that are available to you to use at that specific time. And that's pretty much it. You probably want to keep this environment as clean as possible because it can get cluttered pretty quickly. Okay, and this is just some file management. So because coded data might be difficult to type over and over, we're just gonna put everything in coded data and copy it into a table called data, and then we're gonna remove the original. So we'll be just left with a copy of this that's called data. So Control Enter, Control Enter. All right. Okay, and these are pretty straightforward actually. You can pretty much guess what each of them do just by looking at the equation. And these are to calculate individual effect sizes. So pooled standard deviation, change in control variable, change in experimental variable, hedges G for each row, standard error of hedges G, standard error. And you only need to do this if the data set you have doesn't have like any of the hedges G or effect sizes calculated. And in that case, this actually makes it pretty easy. If they're already complete, then just run this line of code. In my case, all the effect sizes have already been calculated, so I'll just do this to get the standard error, which we'll need for the multi-level meta-analysis. Okay, now we have a full data set complete, but we might not want every single row in that data set, every single column. So to make it easier to use, we typically use something called an intermediate table, and this just separates all the most important parts of the data set into an intermediate table where it's shorter, it's easier to view, and there's no like junk or things that you might not want in the final report. So in this data table, intermediate data.table, again, one of the libraries I imported before, we have a column called hedges G, which is basically just data, like the effect size within the data set we have. Okay, and I'll explain a little bit about what this dollar symbol means. So this just segregates that specific column into a vector and then adds it to this data table. So data $ ES hedges G means that it takes the ES hedges G column within the data set and puts it into a variable called hedges G, which is then put into a table. And you can see that for all of these. Standard error, sampling error, and then these are all of our moderators. So currently we have 10, and you modify the names based on the meta. So within your data, you might have a different name for study ID, gender, new duration. So depending on your meta-analysis, you'd have to change this name. And you probably want to change the variable name too, because then it makes it much less confusing to work with the moderators. So let's just control enter with this. And now you can see we have an intermediate data set. And this is pretty much it. And you can see it's a lot nicer than our normal data set, which had a lot of redundant columns and a lot of empty columns as well. Okay, so now we clear the environment of a bunch of unneeded variables. And the reason I have more here than there are here is because if you ran this code, then that would mean that all of these variables would get put into the environment and it would get cluttered very quickly. So I'm just going to clean it right now. So now we have our original data set and our intermediate data set to work with. Okay, now the actual meta-regression. So normal meta-regression doesn't account for the fact that each individual, like within a study, measurements are not independent from each other, meaning that within a study, if there are multiple measurements, they're all related in some way. You can't just pretend that they're all from different sources or different populations. So this is okay, but it isn't considered as rigorous as a multi-level model. So I'll go over what this does. So this is the metagen function that's provided in dmetar, and I'll go through what all of this is. So we're storing the results of this metagen function within a variable called metacalc, and there's a number of parameters you have to give it in order for it to output anything. So hedges G, within the data set that you provide here, data equals intermediate, so you can see I'm using my intermediate data set. So this is the column that contains the effect size data. This is the column that contains the standard error of hedges G, that data. And I'll explain what this means. So within a fixed, okay, so you can only use a fixed effect model when all included studies come from the same population, but pretty much all the time, if you're doing a meta-analysis, that's not going to be the case. Obviously, all included studies aren't going to come from the same population. They're going to come from all around the world, so it doesn't really make sense to pretend that all of them do come from the same population. So we can't use a fixed effects model, so we have to use a random effects model. that sort of accounts for that. So fixed effect is false and random effect is true. And then method.tau equals REML is this. So basically, this is an estimator that's used when calculating pooled effect sizes. And there's many different ones, but the one most often used in scientific literature is maximum likelihood or restricted error maximum likelihood. And really, if you use any tau squared value, the final result you get is the difference in the final result you get is actually pretty minimal. So this doesn't actually do much, but because the general consensus is to use REML with meta-analyses and multi-level meta-analyses, that's the one we're going to use. HAKN is the okay. Let's see. HAKN is the Hartung Knapp Knapp-Hartung method, and this basically accounts for differences with small sample sizes. So this makes sure that small sample sizes are accounted for in that they don't have too much of a large effect on the final effect size. SM equals SMD, that's just a way for us to output the data. So it's the summary measure we want to calculate. And we can either calculate the mean difference or Hedges G. And for meta-analyses, we typically use Hedges G, so we're going to use SMD. All right, so I'm going to run this, and that outputs a huge list into a variable called metacalc. And if you want to take a closer look at that list, just like in an easier way to see, in a more convenient display, we just do summary and in parentheses metacalc. And you can see here with the random effects model, our effect size is 0.3022. So it's not huge, but it's something that does somewhat account for variability. So, and we also get a 95% confidence interval here, and a fairly small p-value. That's which shows that it is significant, and some variability. A good portion of the variability in anger can be explained by exercise. Okay, and this is a multi-level model, and we're segregating by ID here, by study ID. So what this does is it clusters every single study into a specific group, and it conducts separate meta-analyses within each group. Then it combines all of those effect sizes into one, depending on the size of each study. So, for example, studies with a larger number of participants would get weighted heavier in their overall effect size than studies with fewer participants. All right, so we're going to segregate by ID, MLCalc, and this follows virtually the same format as the previous function, metagen. In that random, this basically says that we're using the random estimator and we're segregating by my ID. Right, so TDIS is just the Knapp-Hartung estimator, again, accounting for small sample sizes. And our data set to be used is intermediate. And again, we're using the restricted error maximum likelihood method. So it's been run. Let's look at a summary. And our effect size has actually gotten larger, 0.3642. And now let's remove my ID. Okay, so now you're probably wondering, why would our effect size get larger if we're accounting for each study not being independent within itself? And the reason for that depends on your data set. For example, if we actually look at our data set, studies with fewer measurements done, for example, a study with ID 7, they have huge Hedges G values. This one has a Hedges G of 20, which is a clear outlier. So if we assume that each of these measurements are independent from each other, we would expect that the pooled Hedges G is smaller in the event that all of these smaller Hedges G values could cancel out this one. But now that we're accumulating all of these ID numbers into one, it effectively decreases the effect of these hedges G values and increases the effect of this one and many other small studies. For example, this one too. This one has a fairly large effect size. So whether or not the effect size increases or decreases after you apply multi-level modeling is dependent on your data set. For example, if your data set has many small studies with large effect sizes, that means that your effect size is likely to increase after you add another level of regression. However, if your study contains many large studies with many small effect sizes that are overall even, you would likely expect that the effect size decreases after.